Hello there, all my Chem Complete students. Today we are going to take a look at a very interesting topic, which is what do I need in order to pass organic chemistry? So organic chemistry is always one of those weed out courses. It's the one that's usually feared the most and renowned, right, in college courses when you start doing pre-med or some other sort of science, pre-vet, pharmacy, right? Organic chemistry is the one that people always are like, I don't know if I'm going to be able to get through that one. That's the tough one. So let's take a look at what are you going to need in order to pass organic chemistry, and how can you prepare coming from a general chemistry course with limited background in preparation for organic chemistry. So that's what this lecture is going to discuss. We're going to go over the top 5 things that you're going to need in order to be successful in organic chemistry, and these are skills that you should have been exposed to in general chemistry and you can buff up on. So that all starts right now. All right, so the top 5 essential general chemistry skills, what are they and what should we really be focused on? Because there was a lot of material that you were exposed to in general chemistry, and it turns out that a lot of it is important for organic chemistry, but there's also quite a bit of it, I don't want to say that isn't important, but that's not going to apply to your success in organic chemistry the same way it might in another course. So there's a whole lot of math in general chemistry too. A lot of the math tends to go on towards analytical chemistry and a bit of physical chemistry, whereas organic chemistry is going to have a heavier theoretical background, at least when you're first being exposed to it at the undergraduate level. All right, so before I start with the 5 skills here, I just want to mention, if you head over to our website at chemcomplete.com and you go to buy guides, I have taken the time and I have a brand new guide up, how to prepare for and pass organic chemistry. So this is the complement, the long guide that goes to this video. So thank you so much to everybody who has been showing support to the channel, buying the gas chromatography guides. There's been a lot of buying for the unknown organic spectroscopy. I really appreciate all the support. If you want to continue to support, or maybe this is a topic that's particularly of interest to you, you've just found the channel, check this guide out. It's only $10. It took quite a bit of time to write. It's far more detailed than anything I can put into this one video. And it's going to go over these 5 points, but it's going to outline it in multiple paragraphs. It's about a 20-page guide. It's packed full of information on how you can prepare and pass organic chemistry. So I encourage you to go over there. It's definitely worth the $10. You'll get a lot of information regarding what you should focus on in preparing for your organic chemistry class. All right, so skill number 5, you need to know acid-base chemistry. And I want to specify this here, okay, because acid-base chemistry is a huge topic, right? We talk about titrations, we talk about buffers, we talk about Lewis acids and bases. There's just an enormous amount of information, okay? So the main points that you want to understand with acid-base chemistry is, number 1, you definitely need to understand Lewis structures. And Lewis structures specifically meaning Lewis acids and Lewis bases. So remember, we can define them as Arrhenius acids or bases. That's when they just either give off an H plus or they give off an OH minus, a hydroxide ion in water. Then you've got the Bronsted-Lowry. That expands the definition. So Bronsted-Lowry is going to say that it's anything that donates an H plus in solution is going to be considered acidic. That's kind of similar, but for Arrhenius it was only in water. And then a base is anything that accepts a proton. So now things like amines, okay, or NH3, right, ammonia, could be considered a base, whereas before it couldn't, because it could not generate hydroxide by itself when dropped in solution very easily. So then we go and we expand beyond that, and that is the Lewis definition. And the Lewis definition is very important to your success in organic chemistry. You need to understand that things that are a base are going to be donating electrons, and things that are going to be an acid will be receiving electrons. And there's going to be a central theme that you see throughout all of this, which is electrons. I'm going to keep going back and talking about electrons, right? And that's because that's what chemistry is. At the heart of chemistry, especially when you want to take a look at reactions, and that's mostly what organic chemistry is. We study tons and tons of organic chemistry reactions. Okay, it is the movement of electrons. Electrons are constantly being shuttled back and forth to break bonds and make bonds. And so having a general understanding of how Lewis acids and Lewis bases behave, because they do the same thing. A Lewis base gives its electrons, it donates its electrons, and the Lewis acid accepts the electrons. That behavior is very important to understand, because it's going to be the groundwork and the fundamental needed ability that you will require in order to solve organic chemistry reactions. Okay, so this is also going to help you identify functional groups, if you see this other point down here. So when you take a look at organic chemistry, it's broken up into functional groups when you get to the later chapters. So you're going to have a chapter on alcohols, you'll have a chapter on carboxylic acids, you'll have a chapter on esters, you'll have a chapter on amines, right? Well, if you understand acid-base behavior, it can also help identify how is a specific functional group generally going to behave. Carboxylic acids will definitely be acidic, right? Amines will definitely be basic. They're going to act like a base. Alcohols can end up acting like both, so they can be an acid or a base, and the term we use for that is amphoteric. Okay, so it depends on the situation that you put them in. Sometimes they're going to act as a base, sometimes they're going to act as an acid, depending on what medium they're found in. So this is very important, because when you start grouping functional groups together, they're going to usually undergo similar types of reactions, right? So a carbonyl, a C double bond O, it turns out that the carbon has a partial positive formation because the oxygen, which is electronegative, has a partial negative, right? And so that means if it's partially positive, it acts more as a Lewis acid, so it will accept electrons from incoming groups. And sure enough, if you look at most of the reactions for carbonyls, C double bond O groups, right, they have a tendency to sort of push these electrons up onto the oxygen, the pi electrons, and then they accept any sort of incoming nucleophile or electron-dense group, a base that's coming in. So, very important. Okay, why else is acid-base chemistry important? Acid and base chemistry can explain the reactivity of certain organic compounds over others. So an example here is leaving group behavior. Now, if you have not taken organic chemistry yet, you may be like, what are you talking about, right? But you hopefully have learned the various types of reactions, and one of those types is a substitution, and that's essentially what's going to happen here. Another group's going to come in, and you're going to kick a group off, and that'll be a substitution reaction, okay? Now, it turns out certain groups can leave very, very well in order to promote the incoming group and the substitution behavior, and there's other groups that almost never leave. And the answer as to why this happens really has to do with the reactivity of the group once it has departed and gone into solution. So, for instance, I have two examples here, chlorine and hydroxide, right? Chlorine leaves and you have Cl minus, the anion, in solution. And then hydroxide leaves and you have OH minus sitting in solution. Well, it turns out that groups, when they leave, they make a far better leaving group and they participate well in this type of behavior if they are a weak base. Strong bases do not do well with this type of behavior. And if that makes sense, if you think about it, right? If something gets kicked off and it's sitting in solution by itself, in general, it's going to need to be stable. And it turns out that chlorine, as a weak base, is pretty stable because its conjugate acid is HCl. HCl is a very strong acid, and conjugate strength is inverse, right? So if HCl is very strong, Cl minus is very weak. And so it makes a very good leaving group. Now, why are hydroxides not a good leaving group? Well, if I look at the conjugate of hydroxide is H2O. H2O is a very weak acid. That means hydroxide is a very strong base. And because it's a very strong base, it's going to be extremely reactive. It's not going to work very well as a leaving group. Okay, there's a little bit of other reasons in there regarding electronegativity and atomic radius size, but the biggest correlation we have with leaving groups is, Are they a weak base or are they a strong base? And the weaker they are, the better they leave. Okay, skill number 4. You must understand hybridization. I was almost hesitant to put this one in here, but it is so important it had to make the list. Now, the reason I was hesitant to put it in is that I am aware there are a lot of general chemistry teachers out there that as you start to learn this, it's usually around the time that you're doing Lewis structures and then you start learning molecular geometry. There are a lot of instructors out there that just say hybridization exists and then they kind of move on from it. They do the same with resonance. They don't really discuss it. You don't really understand what's going on, okay? I'm not going to give a great detailed breakdown here. I do that over with the guide. So if you pick up the guide, I go into far more detail about what is hybridization, why does it occur, okay? In a very brief summary, hybridization is the merging of orbitals. So you have s, p, d, and f orbitals, right? So carbon has s and p. So what happens is when carbon is ready to bond, it takes its s orbitals and its p orbitals, and it kind of merges them or crunches them together to create these new hybrid orbitals. And there's energy reasons it does this. It makes for a more stable energy. And one of the big reasons they propose is that it's better overlap. So when you've got an S and a P that tries to come together, they're a mismatch as far as their shape. But if you hybridize them all to the same shape, then there tends to be better overlap with other individual incoming atoms, right? And hybridization occurs in order to promote better bonding and better overlap. So those electrons are shared to a greater degree. Okay? Now, if you have been exposed to hybridization, or if you've taken organic chemistry before, you know there's sp, sp2, and sp3. And you can go up to the Ds. So you can have sp3d, but we're not getting into that because in organic we focus on carbon, and carbon is S and P, right? And a lot of the other surrounding atoms are, right? So hydrogen can't even hybridize. It only can have S because it doesn't have any p orbitals. And then oxygen and nitrogen, they have lone pairs. And again, I talk about all this in the guide. How do you determine if it's sp, sp2, sp3, etc.? Okay, but when you take a look at that, most of the elements in organic chemistry are going to be sp, sp2, or sp3, right? And in general terms, they will be sp hybrids. There's not going to be Ds in there. So hybridization is going to help you understand carbon bonds. And this is important when you're starting to look at single bonds versus pi bonds, and pi being double or triple bonds. Hopefully that's something you were exposed to in general chemistry. Okay. Now, hybridization many times explains reactivity and stability of certain organic compounds. And a perfect example of this, we can take a look at this quickly, is some functional groups. So if you have alkynes, which are carbon-carbon triple bonds, and then there is a hydrogen attached, and then you take a look at alkenes, which are carbon-carbon double bonds with hydrogens attached. All right, if you take a look at this proton, and then you take a look at these protons, this one is going to be far more acidic. Okay, and these will be less so. So that you can consider they have mild acidity, but this will be less acidic than the other one. Now the question is why? Well, as this leaves, as the hydrogen departs and becomes an acidic proton, the electrons from the bond go to the more electronegative element, which is carbon. Okay, and what you're left with is a anion, a formal charge buildup. All right. Now, if you take a look at the hybridization here, okay, the hybridization that is left behind, this type of bond is going to be sp, whereas this one would be sp2. Okay, and S is 50%. I'm sorry, sp is 50% S in nature and 50% P in nature. Whereas sp2 is going to be, and these are approximate numbers, right? 33.3% S and 66 point, we'll just say 7 for good math, percent P. All right, so what this means is that you have more S characteristics in the alkyne than you do in the alkene. Okay, and what's important about S? Well, the S orbital is closer to and hugs the nucleus better. And what's in the nucleus? positive charges, protons. So that means that this leftover set of excess electrons that lead to the formal negative charge are going to be closer to the central positive force, and that helps to ground or stabilize that charge that's left behind, right? So you only get about 33% of that effect here, whereas you get 50% of that effect here. You've got more S characteristic. And because of that, that helps to explain why this group is more acidic versus this group right here. Okay, so again, in the guide, I talk about that in a bit more detail. So you're welcome to pick that up if you want to see some other examples and get a better understanding. I also discuss how do you determine SP, SP2, and SP3. If you want to know how to do that, I've got other videos on the channel you can look at for free. Okay. One other thing I wanted to mention. You want to know this because this is some of the most confusing material, and it's also usually presented first at the very beginning of organic chemistry. So we'll look at skill number 3 in a second. I wanted to show you, this is one of the most popular videos I have on my YouTube channel. And this video is, are lone pairs in hybrid orbitals? Okay, so when you get to nitrogens, oxygens, a lot of students are completely confused. Is it in a hybrid orbital, like an sp3 orbital, or is it going to be considered in a p orbital, right? And this usually starts talking about aromaticity and resonance and a couple other things. But this is one of the most popular videos on my channel to date. And it's because this is a difficult concept, but it comes up over and over again in organic chemistry. You must understand hybridization. All right, skill number 3. And this is a general statement that you should apply to all your chemistry courses, but it's amazing how many people keep forgetting this fact, even when they get towards the end of organic chemistry. You must be able to correlate energy and stability, okay? So energy and stability have an inverse relationship. That means as one goes up, other one goes down. And that is very, very important to comprehend when you're dealing with bonds, atoms, molecules, reactions, intermediates, anything. Anything that you come across, you need to understand this principle, okay? So stability and ground state energy will often explain why certain organic compounds will react the way they do. So why are some compounds more reactive than others? Because their energy is higher, so they're less stable. They want to react and go into a more stable state, okay? So you can see here, consider the example of why carboxylic acids are deprotonated more readily than alcohols are. When a carboxylic acid is deprotonated, it leaves behind a high-energy ionized oxygen. This ion is stabilized through delocalization of charge over an additional oxygen, and that benefit is not available to the alcohol. So that's a long-winded way of saying you get resonance. There's resonance, all right? So what does this look like? Let's actually take a look here. Okay, so what resonance looks like in this example here. So let's draw... Okay, carboxylic acid, we'll just go with acetic acid, right? So you've got this, and then you've got, we'll use ethanol, right? So pretty similar. All right. So you've got this going on, and what comes out is the following. You've got an O- here. Okay, showing the lone pairs here. I got to do that up here too. And then here it is for ethanol. Okay, now something that's important to understand here is resonance is going on. Now again, I'm not explaining resonance in great detail. I'm telling you what you need to know in order to pass organic chemistry. But here's the fact that you have a negative charge that is in proximity to a set of pi electrons, it can form a pi bond, and these pi electrons can deposit up on this oxygen. This oxygen, for the ethanol, that should be a minus charge there, does not have that ability. This oxygen has to just sit here with the negative charge, whereas this oxygen has the ability to pass the negative charge, almost like a volleyball game, okay, back and forth with its partner. And so you end up with another form that can look like this. Now what happens in reality is that there aren't these two individual forms. Hey, the electron sort of takes up position between the two forms, and it's spread out, delocalized, okay? But what's happening here is that this is a sign of stability. Okay, because when we take a look at stability, when we take a look at charges, okay, if you have a charge, formal charges are not considered very stable. And so to dump them on a single element is not ideal. You want to be able to spread that charge out and have several different elements that are able to help assist with that formal charge buildup. All right, so that's an important point. You need to understand energy and stability and how as one goes up, the other goes down. Now, there's other factors to consider here. So you can talk about sterics, you can talk about carbocation formation, and we discuss all that in the guide. All right, but in general, you need to have a very good understanding of the fact that energy and stability have this inverse correlation. It explains a lot of what's going on behind the scenes. All right, number 2, you need to know the trends of electronegativity. Electronegativity is a common periodic trend that's taught in general chemistry, right? You go to the bottom left of the periodic table, you go up until you hit fluorine and the noble gases drop off with that. So electronegativity is essentially going to be how effectively does an element, a particular type of atom, pull electrons in towards itself. This is very important when you get to organic chemistry. Okay? Now, one of the reasons for this is that it's going to allow you to predict where there are positive and negative electron buildup. So positive means there's a lack of electrons there, right? So you could call that a partial positive buildup, whereas negative means there's a lot of electron density starting to accumulate in one area. And this is extremely important because when you originally look at a reaction, an organic chemistry reaction, you're just going to see a whole bunch of different atoms that are kind of strung together. And if you want to know how they react without just memorizing it, you need to find the sources of partial positive charge and the sources of partial negative charge because, right, they're going to go together. The negatives are going to seek out the positives and likes are going to repel. So negative and negative, they won't go together well, but the opposites will attract. You're going to have the partial negative or the full negative, formal charge negative materials coming into the partial positives or the full positive charges. So you need to understand electronegativity because you are able to do this better if you have a grasp of electronegativity. So take a look here. Okay, here's a common organic reaction called the Grignard reaction. Now, you have two choices. Are you going to memorize or actually comprehend how this works? So, if we go through the first path, just look at the very top part of the screen here without the arrows. This is what you write on a flashcard. This may not make sense to you, and you're forced to just tuck it into your memory. All right. Now, what happens if I start labeling where all the partial positives and partial negatives are? So let's take a look at what's over the arrow. Metals always take on a positive or partial positive charge. So magnesium is partial positive. Okay, that means what's around it is partially negative, including the carbon here, okay, that would be coupled up with it. And the hydrogen down here has a formal plus. Now, if I come over to this structure here, and again, if you've never taken organic, it's okay. I know this looks overwhelming right now. Just follow along with what we're saying, okay? So, carbon, and then oxygen. So this little dot, or this little tip of a triangle here, that represents a carbon in between the two CH3s. Okay, well, if I look at the electronegativity values for carbon and for oxygen, there's a difference, a pretty big difference between them, and I get a partial positive on the carbon, and the electrons tend to gravitate or head towards the oxygen. So that separates the charge. Well, now I'm in business because I've got a partial positive and a partial negative, right, by the C double bond O, and then in the reagent that's supposed to behave or react with it, I have a partial negative part and a partial positive part. So it only makes sense that the partial negative would come into the partial positive, right? The partial negative is not going to come into another partial negative since electrons repel. Because what that's stating is that the oxygen already has a decent amount of electron buildup, and the CH3 in this reagent over the arrow, the CH3 MgBr, also has a decent amount of electron buildup. So why on earth would two giant chunks of electrons sort of come together and meld? It's not going to happen very readily. That would be a destabilizing high energy situation like we just talked about. It would make much more sense that it comes into the partial positive, and once that happens, we can take a look at what would occur And then in the second step, the oxygen has a negative because this bond had to move out of the way so that carbon could form 4 bonds here. Okay, and then this oxygen seeks out its positive by finding that in the second step, and then we have the reagent. Now, the formal term for this is a mechanism. Okay, it's the mechanics of how the reaction works, and they call them organic mechanisms. In order to complete organic mechanisms and understand what's going on with your reaction, you want to have a understanding of electronegativity. Very important skill. Okay, and skill number 1, you can really view this as a summary of the last skills, but it is the crowning skill. It is the most important skill. It summarizes all of it. You must understand how electrons behave. Electron behavior drives all of organic chemistry. It really drives most of all of chemistry, okay? But in organic chemistry, because we're really focused on theory and we're leaving a lot of the math out, you need to understand the theory of how electrons behave. So all other skills in the list revolve around that premise, and it's the ability to understand how electrons behave. Okay, organic chemistry is going to look at a lot of this. You're constantly going to be moving electrons back and forth, breaking bonds and forming bonds. Okay, so a couple of points here, and we're going to try to wrap up because we're getting close to 25 minutes now. All right. Knowing electrons have a negative charge and repel one another allows you to understand sterics. I mentioned sterics a few minutes ago. Okay, so this term is used to explain certain organic phenomenon when electron sets get too close in proximity. So to give you an idea of what this is talking about, and we go into sterics in great detail in the guide. Okay, sterics, if you take a look at it, is essentially saying every time you're piling up larger groups of electrons, you're going to run into less stability, and you're probably going to shut down certain pathways that are trying to use this. So here's an example. Here's a carbon. It's got 3 hydrogens, right? And then it's just got this one CH3 group up here. Hydrogens aren't too bad, so they're not going to interfere too much. But what happens when I start building up, right, the number of CH3 groups? Because these are pretty bulky in comparison. So let's say now I put another one here. Well, now we're starting to get a little close, right? And then let's say I have another one down here and we only have one single hydrogen right here, like this. Well, this is a problem because we've got very close, right? Here's a CH3 group. Okay, here's our little isolated hydrogen. Here's a CH3 group. Here's a CH3 group. It is starting to get not just visually crowded, but electronically crowded because each of these bonds that we have here are considered electrons, and they are piling up. So people that may have taken organic chemistry or are in the process of, and you don't understand sterics, this is sterics. Sterics is referring to the fact that you have way too much, okay, too much electron property in one area. It needs to be spread out more, okay, because again, electrons are negative, so you put a whole bunch of them next to one another, then you're going to have issues. So yeah, that's occurring to some extent here, but these bonds try to separate themselves as best as possible, right? And then they get breathing room on either side here. But when we don't allow for that breathing room and we just keep piling in, right, we're taking a whole bunch of them and kind of just jamming them in a small area. And in general, molecules aren't going to be okay with that, okay? Now, sometimes it's going to happen, and there's other things that we can look at regarding their ability to use hyperconjugation, and they go through a carbocation then instead of some other forms. But that's for a different topic, all right? That's the general idea behind sterics. So electrons are drawn in by atoms with more protons in their nucleus. This is the periodic trend. So in other words, this is electronegativity. That's partly how electrons behave. You have to understand where electrons would prefer move or gravitate towards, and that has to do with electronegativity. So again, this is primarily going to be a summary of a lot of the other stuff that we had on this list. Okay, electrons are responsible for all bonding. Knowing this will allow you to locate regions of electron density and properly move them. Okay, there is a very important point at the very end of this slide. Cations do not make the first move. It is the anions that do so. And what that means is that anytime I have something with a positive charge and something with a negative charge, okay, and this, you can apply this to partial positive and partial negative, right? So meaning, we saw examples where there was something like here's partial negative, oops, and that's a delta plus, right? Same thing applies here. Anytime that you do this, the electrons make the move to the lack of electrons, okay? This is the way you go. You don't ever write your mechanisms like this, where the H plus is headed to the negative. That's not the way that this works, because what you're saying here in the first example is you're saying these electrons move to fill a void where electrons are needed, okay? And what this says is that a void which does not have any electrons is moving in order to take some of these electrons, okay? It's always the first way. This is the way that all organic mechanisms happen. And if you look at examples, you're always going to see every time an arrow originates, meaning its source right here, it's always going to originate from a source of electrons, whether that's a bond or whether that's a lone pair. You're never just going to see partial positives or fully positives initiating reactions. All right, that is it. So I'm definitely going to bring it to a close here. Remember, head on over to chemcomplete.com, check out that guide. We appreciate your support as always, just watching the videos on our channel, supporting us, dropping a like, interacting with comments, all helpful. If you subscribe, you'll be up to date throughout the semester. And that is it. Let's wrap it up. Good luck in organic chemistry, everybody. This is Professor Tomney from Chem Complete, and I will see you in the next video.